Now let's resume problem 2. Problem 2.1, we did it in the previous video, and this one is tricky. It's about determining sample size. I don't want to go back to that, so let's go over to the next one and review this one. And this part is rather controversial and can be a bit vague, but then again, part of that is statistics. Depending on some people, you may feel entire statistics as rather vague and untidy. Well, it has those kind of nature, to tell the truth. But the idea is, whatever decision you make, you have to explain your reasoning. And here it is. Here's a prime example. Due to the lack of resource, the student managed to interview a simple random sample of just 27 people. They claim the normal distribution is still appropriate in this case. Explain their reasoning. They cannot use the central limit theorem this time because sample size of 27, too small. Central limit theorem requires large sample size. Kind of like this. Has to be about mean, and it has to be random sample, simple random sample, and large sample size. That's how the central limit theorem applies. Now for such a small sample size, you cannot use central limit theorem. But how do these students claim that this distribution is still okay? Well, here it is. It has to be out the mean, and the population is believed to be normally distributed, commute time, original population's commute time distribution, with known standard deviation, and 16.7 minutes came from the previous study, status quo. So we'll just accept status quo as standard deviation of population. That's pretty usual thing to do in statistics. Of course, some people may disagree, and no, we cannot accept status quo. You have to use new one, and consequently, you have to use different method. Yes, there are different paths out there, but if you take that path, you have to make your own reasoning for that path. For this particular reasoning, here it is. It's about the mean, yes, and original distribution is normally distributed, and we have to have known population standard deviation. There are two cases that we can use normal approximation in inferential statistics. One is the previous case, the central limit theorem case, mean, randomness, and large sample. This is completely different case. Mean, of course, yes, but the original population is normally distributed, and we know the original population standard deviation, which usually come from the previous study or status quo. Okay, let's use the student's reasoning and answer 2.3 and 2.4. 2.3. The student sample study yielded the mean commuting time of 48.8 minutes and a standard deviation of 17.3 minutes. Estimate the 95% confidence interval. Whoa, we have another standard deviation coming. Status quo of 16.7 or student's figure of 17.3. Which do we use? Well, if we're going to use this 17.3 and we assume that standard deviation 16.7 is not the one we are going to be using, then we cannot use normal approximation. We'll have to use the t-test, which is going to be topic for chapter 9. But here, student reasoned, we'll still use normal approximation. So that assumption includes that 16.7 will represent the population standard deviation. So we'll use 16.7 instead of 17.3. Tricky, isn't it? Here's the initial picture. 95% in the middle, 2.5%, 2.5%, pretty normal. And here's the technical steps. And minus center over SE is negative 1.96, but in the SE computation, please note that we used 16.7. If you use 17.3, we cannot use normal table. You have to use something else here. Okay. Flip that denominator over to the other side. We get that. Flipped 48.8 to the other side. Do the computation. Change this minus to plus. Use the symmetry, and then we get that. And that's how we get the confidence interval. Remember, in this problem, we have two competing standard deviations, and that causes problem. Now, if you use the sample standard deviation that came up with this very sample, you cannot use the normal table. Oh, excuse me, I take it back. If the sample size is too small, like 27, if it is 2000, it's okay, but small. In that case, you cannot use sample standard deviation and the normal curve at the same time. You'll have to use the t-table or something else if you're going to use this one. But in this case, students are using 16.7 minutes as status quo value and the normal approximation. Based upon that, well, we had the previous computation we did. Now let's go to 2.4. 95% lower confidence bound. Again, we are going to be using the same method, the normal approximation, where standard deviation of population is 16.7. Here's the initial picture. It's lower bound, so less than 48.8, and here's we have 5%. There we have 95%, so we have to look at 5% from the normal table. We have done it before. It is negative 1.645. So we end up with this equation, and looking for x value from here is just routine algebra. In the end, you're going to get 43.51 something, and that is your 95% lower confidence bound. The technical steps behind 2.3 and 2.4 are easy. Just draw the normal picture using the standard process: outline, center, end, and then shade. And then just use the same formula, z equals n minus center over se, and just solve algebraically. That's easy. We have done those before, and will of course do many more times. But the key part was which standard deviation to use, this one or that one, or which approximation we use. The problem explicitly said normal distribution, so there has to be some justification. For small sample size, we're gonna use normal approximation still. Then we are assuming, as a matter of fact, original population is normally distributed to begin with, and the population standard deviation is known. Here is short version, by the way. Population standard deviation is assumed as status quo value.